The Global Positioning System is a network of satellites and receiving devices used to determine the location of something on Earth. Satellites send out signals at all times containing their locations and the time. When receivers intercept the radio signals, they use multilateration to calculate their location with a precision of around 5 meters, which is quite impressive as GPS satellites orbit at an altitude of more than 20,000 kilometers. The car had received 3 signals that came from 3 satellites. The signals contained the time of which the signals were sent, or the time of transmission, and the location of the satellites in the form of X and Y coordinates. The car first needs to calculate its distances from the satellites. To do this, it uses the formula distance equals speed times time. It calculates the time of which the signal is being transmitted, or time of flight, using the formula time of transmission minus time of arrival. The speed of the signal doesn't even need to be calculated. This is because all electromagnetic waves travel at the same speed. Light is also an EM wave, which means the speed of the signal is equal to the speed of light. The distances are then used to construct 3 circles, with them being the radii and the satellites being the origins. The point of intersection happens to be the only point that is 2 units from this satellite, 4 units from this one, and 5 units from this one. This means that the point of intersection must be the location of the car. But wait a second. We may have pinpointed the location of the car, but we still don't know its exact coordinates. Well, yeah, so we can all see that it is at 0, 0, but this is because I'm visualizing it. For computers, there's a faster way to do it without any of this visualization. They calculate the coordinates of the car using a system of equations involving the distance formula. In this scenario, where the world is 2-dimensional, the distance formula between the car and the satellite is this. This equation is actually derived from the Pythagorean theorem, where you're solving for the hypotenuse, c. In other words, the distance we're trying to calculate is c, because the sides A and B are the 2 sides of the triangle that lie on the straight lines of this imaginary grid. We can then use Pythagorean theorem as it forms a right triangle. To solve for c, we need to isolate c, like this. As previously stated, sides A and B are part of the grid the coordinates lie on. A, therefore, equals to x1 minus x2, and B equals y1 minus y2. We can now substitute A, B, and C with their respective definitions in this context. C is the distance, A is x1 minus x2, and B is y1 minus y2. There, we now have just proven how the distance formula is derived from the Pythagorean theorem. We know the satellite's coordinates and their respective distances to the car. Since there are 3 satellites, we can make 3 different equations using the distance formula, with the only unknowns being the coordinates of the car. We can then solve this system of equations. Now, all of this might seem impractically time-consuming, but in reality, all of this will take less than 0.05 seconds. In the real world, there are 3 dimensions, and therefore the circles would then be spheres. The 3 spheres narrow the possible locations down to 2. The addition of a 4th one will give us the car's exact location. We again use the distance formula to calculate the coordinates of the car. However, the distance formula needs to be a bit different to accommodate for the extra dimension. To represent the extra dimension, we add an extra variable, z, into the formula, like this. We do this because a squared plus b squared acts as the width of the triangle, and plus z squared is the height. Since we have 4 satellites, we'll have 4 different equations. and now we calculate. Of course, cars aren't the only things that benefit from GPS. The most widespread use of GPS is for logistics and transportation. Companies can keep track of the location of their goods, and individuals can receive traffic and navigational information. In terms of social justice, utility companies can respond better to outages with GPS to track and maintain their network of services. Sometimes GPS signals can miss their target and reflect off the ground. Scientists thought the reflection was simply noise for a while. However, with the help of machine learning to analyze the reflected signals, they eventually realized that the reflection reflect qualities of the surface it hit. If the GPS signal was reflected off of snow, it'll be different than if it was to reflect off of grass, for example. In terms of applications, this allows agricultural companies to collect information such as soil composition, which aids them in managing their fields better. GPS is also used in the military to help guide the troops and vehicles. This requires the GPS to be more accurate and precise than its civilian counterparts, which is why the military uses 2 GPS frequencies instead of 1 GPS frequency. This will correct signal distortions caused by, say, the weather, the humidity, and atmosphere as much as possible. The accuracy of GPS is closely related to the location of the 24 GPS satellites, namely when they're closely grouped. If that's the case, small errors in the calculation of the satellite's position are magnified and will have a large impact on the accuracy. For reference, this is when the satellites are spread out. Although the error in the calculations of the satellite's position is the same, the difference between the car's position and its calculated position is greatly reduced. Not to mention, having a close grouping of satellites just isn't very efficient. Less ground is covered this way, and it's harder for people living in urban canyons, where there are tall obstructions, tall buildings, to receive the satellite's signals. The Earth itself physically alters the satellite's orbits, and therefore the satellite's positions. What do I mean by this? Well, it means that the satellite has to predict its orbit as accurately as possible. What if the satellite treats its orbit as a perfect circle? This is no good, because the Earth is only approximately a sphere. It's realistically more like an ellipsoid, which makes the satellite's orbits effectively oval-shaped most of the time. Then, what if the satellite treats its orbit as a perfect ellipse? Again, because the Earth is not a perfect sphere and it has uneven mass distribution, the orbit path of the satellites may be affected by the differences in gravity. This requires the satellite to take into consideration the topology of the Earth. At this point, the error between the satellite's actual position and its calculated position based on its predicted orbit is minuscule. However, although it is small, if left uncorrected, it may cause the satellite's calculation to become more and more inaccurate over time, to a point where it may escape its orbit and fly off into space or crash down onto Earth. That being said, how can we enhance the precision of GPS? How can we prevent GPS satellites from falling down onto Earth or flying off into space due to errors in its calculations? Well, as I have said before, utilizing 2 GPS frequencies will enable us to spot errors and hence enhance the overall precision. Another common approach to precision enhancement is to use something called differential GPS, which corrects the calculated positions of satellites. DGPS works by having multiple stations on the surface of the Earth that contain its exact coordinates. Satellites can correct what they think their locations are by calculating what they think the coordinates of the station is. This is then compared to the actual coordinates of the stations, and the difference of the two values is then also the difference between the satellite's actual position and the satellite's calculation of its actual position. And therefore, through simple subtraction, we can get the satellite's actual coordinates. As we all know, food deserts is a prevailing social justice problem. Without access to fresh, good quality food, impoverished areas are subjected to hunger, poor diets, obesity, and other diet-related illnesses. The problem of food deserts can be split down into two smaller problems that ultimately create food deserts. First, it usually takes a very long time to get to the nearest healthy food spot in food deserts, such as grocery stores. This de-incentivizes a lot of people who may be too busy or too lazy to spend that extra time to drive to those grocery stores, and instead opt for things like fast food restaurants to satiate their need for nourishment. Second, there may simply not be enough supply. Maybe the local farmers are working hard to grow healthy vegetables and fruits for the people's consumption, but the yield, and therefore their price tag, is just not enough to compete with other food choices. This lowers supply as the number of local farmers dwindles. With the help of GPS, though, we can implement machine learning that analyzes the GPS data to help optimize the travel routes and their time. This is especially true if people are going on foot, as this opens up more possibilities for the path taken. The existing assets for this are already implemented since GPS is intended to be used for improving navigation. Additionally, GPS systems we already use, such as Google Maps, can provide us with these updated, more efficient travel routes that we can take to reach healthier food spots. As for the supply problem, we can simply increase the supply by increasing the yield. As previously stated, GPS is capable of monitoring soil quality. This can be further applied to the idea of precision agriculture, which is, in short, a strategy that uses monitoring to allocate resources and therefore increase the overall crop yield. In our context, we can use GPS to optimize the use of resources, such as water and fertilizer, based on the monitored soil quality and data maps created using GPS. Farmers can also make long-term decisions based on the trends they observe through monitoring. For example, they may decide to limit the leaching of nitrogen as to not contaminate underground water sources. Essentially, we increase productivity and enhance the farmer's decision-making both in the short term and the long term through GPS monitoring. With these two problems addressed, we can hopefully contribute to alleviating the food desert issue.